Guys. So this is the lecture series on digital image processing, and from the last class, we are discussing about data compression and image compression techniques. Okay, so we have seen some types of data redundancies in the last lectures. So let's begin from there then. So you've seen that we have coding redundancy, spatial redundancy, and irrelevant information. Okay, so this pictures, this the first one represents our coding redundancy, second one is the spatial redundancy, and third one is the irrelevant information. So today's first question for you, as you have already attended the last lecture, so you know that what is coding redundancy, what is spatial redundancy, and what is irrelevant information. These are the three different types of data redundancy. So define each of them through comment. You give the answer, means the definition of this coding redundancy, spatial redundancy, and irrelevant information. So let's start today's class. So you see that coding redundancy, say the discrete random variable for rk in the interval 0, 1 that represent the gray levels. Each rk occurs with a probability, say pk. If the number of bits used to represent each value of rk by L of Rk, then we'll have L average as is equal to K goes from 0 to L minus 1, LRK and PRK. Okay, then the average code bits assigned to the grave levels, and the length of code should be inversely proportional to its probability. Now, one example of variable length encoding is this one. So we are considering different values of RK. Similarly, with respect to we have this PRRK, then code, then LRK, code 2, L2RK. So they just take a screenshot. It's not going to play important role in this lecture. Just take a screenshot of this. Then spatial or temporal redundancy. So internal correlation between the pixel result from say respective autocorrelation, structural relationship, and geometric relationship. Okay, these are the reasons. Then the value of a pixel can be reasonably predicted from the value of its neighbors. And to reduce the interpixel redundancies in an image to the 2D array is transformed or mapped into more efficient form, that is frequency domain. Okay, and about that information transformation, okay, image transformation, I have given assignment, so I hope all of you have attempted it. So try to means have a study on those different image transformation techniques. Okay, because they are very important for us. Then we have irrelevant information. So what actually we are talking as from the this about this type of redundancies with respect to our image data. Okay, so irrelevant information and psychovisual redundancy. The brightness of a region depend on other factors that the light reflection. The perceived intensity of the eye is limited and non-linear. Certain information has less relative importance than other information in normal visual processing. So in general, observer searches for distinguishing features such as edges and textual regions. So these are the information related to means coding redundancy with respect to image. Then we have our spatial redundancy with respect to image. Then we have our irrelevant informations with respect to image. Now, how to measure image information? You know how few bits are actually needed to represent the information in an image. Is there a minimum amount of data that is sufficient to describe an image without losing information? So these two questions always comes to our mind. An answer will be given by information theory. I hope in your machine learning lecture you are already familiar with this term information theory. So that this is the formula basically. I is equal to logarithm of 1 by p, that is minus of logarithm of e. So this units of information. This will be given by this formula. So if the base 2 is selected, the unit of information is the bit. Okay. Given a source of statistically independent random events from a discrete set of possible events, say A1, A2, AJ, with associated probabilities, say P of A1, P of A2 up to P of AJ, then the average information per source output will be known as the entropy of the source. Okay, and that will be given by H is equal to minus J goes from 0 to K. Okay, P of Aj, that is probability of Aj, into logarithm of P of Aj. And believe me, this entropy information is very much means important for you. Okay, do note down this the formula of entropy. Here Aj is called source symbol, and because they are statistically independent, the source itself is a zero memory source. Okay, so that's how we measure image information. So this information is totally dependent on entropy. Now, for image, we use the normalized histogram to generate the source probability, which leads to the entropy. This is the formula, and here H for previous examples is, say, for the first image is 1.6614, and for H for the second image is 8 bits per pixel. So H for third image will be 1.566 bits per pixel. Okay, so these values you can easily calculate by putting the respective values in this formula, or suppose you have a function entropy in MATLAB, and using that function you can calculate the value for the entropy. Okay, I hope these are the information sufficient for this lecture. And just in this lecture, main point is that what is entropy? Okay, so try to answer the question that what do you mean by entropy and how it helps to means collect information about an image. Okay, so repeating the question again, what is entropy? Okay, then how entropy helps us to gather image information. So try to answer this question, and that's all for this lecture.